Hi, I want to talk a little bit about the problem that we ended up with at the end of the first lecture this week. So this is the bridges of Königsberg problem. And the problem was, can we find a circuit in this pseudograph below? So it's a pseudograph because there are, I'm supposed to say it's a pseudograph because some pairs of vertices have more than one edge between them, like there are two edges between vertices A and B. Can we find a circuit that uses every edge? Let's see what would happen if we tried. Suppose the circuit started and ended at A. Well, if it starts at A, we have to take some edge out of A, right? And then we know that whatever we do, we'd have to use the other two edges that come out of A, or that are adjacent to A. One of those edges would be an in, and then the other one has to be an out. And so we see we can never start at A, leave A, use all of the edges adjacent to A, and exactly once, and end up back at A, because we have an odd number of edges at A, right? So that whatever the first vertex of this circuit is, it would have, the edges at it would have to pair. We'd have to go out, come in, go out, come in, eventually. So there'd be out, in, out, in, out, in, and it would have to end on an in. So you'd have to have an even number of edges at the first vertex. And if you think about the intermediary vertices, the same thing would have to happen, except for the intermediary ones, we would come in, then we'd have to get out, and then so they'd pair in, out, in, out, in, out. But if there are an odd number of edges there, at some point we'd go in and we wouldn't be able to get back out. Okay, so what's kind of amazing is that this argument generalizes. So recall that a graph has an Eulerian circuit. A graph has an Eulerian circuit if it contains a circuit using every edge, and because it's a circuit, we would have to use every edge only once, okay? An example of a graph with an Eulerian circuit. So here's some examples, like our favorite example that we've seen before, the bow tie. This graph has an Eulerian circuit. If I name these vertices A, B, C, D, E, we can see we can traverse all the edges if we start at A, for example, by going to B, C, D, E, C, A. I see the vertex C twice on this circuit in the middle, but that's okay. Circuits can reuse vertices, they just can't reuse edges. So here, this is an Eulerian circuit. A, B, C, D, E, C, A is an Eulerian circuit. And the kind of amazing thing is that the thing that we observed in the Königsberg example, that if I have a vertex of odd degree, I'll get stuck at it. If I leave it, if it's the first vertex, I'll never be able to return to it and stay there having used all the edges. And if it's an intermediary vertex in my circuit, I'd never be able to, at some point I'd get stuck and not be able to leave it. So that property actually determines whether or not a graph has an Eulerian circuit. So what do I mean by that? What I mean is that there's a theorem that says G has an Eulerian circuit if and only if every vertex in G has even degree. Okay, so oops, look, there's a little something there that shouldn't be there. I'm gonna get rid of it. So what's amazing, I think, one direction of this theorem is a lot easier than the other. One we've essentially argued already. So that's the forwards direction. Okay, so I'm going to write that down. So suppose that G has an Eulerian. Suppose it has an Eulerian circuit, and then I'll say then the first vertex in the circuit has edges that have to pair up as leaving the vertex going out, coming in. So out, in, out, in, out, in, and the last one has to be in. And the intermediary vertices have edges that must pair up, where I have to come, if it's an intermediary vertex, I come in and then I have to get out again. So they pair up as in-outs. Okay, so because I don't get stuck at any vertex in the middle, and I can eventually come back to my starting vertex having used all the edges adjacent to it, the edges at each vertex have to pair as outs and ins or ins and outs. Okay. All right, and now let's try the other direction of the proof. This one's more involved, so I've written it out and then I'll explain it. We'll go over it now and then I'll do an example. Okay, so for the other direction, suppose G is connected and every vertex has even degree. So what I'm going to do is I'm just going to start at an arbitrary vertex V, and I'm going to construct a circuit that's Eulerian, that uses every single edge and starts and ends at that vertex V. Okay, so what I'm going to do is I'm just going to start following a trail from V. Okay, I know, and every time I encounter a new vertex on that trail, I go in, but because it has even degree, I can go out, and I'm pairing those edges as in-out pairs. So every time we visit a vertex, I can also leave because they have even degree. And since there are only finitely many vertices, eventually, well, if I keep coming in and going out and coming in and going out as much as I can, as long as I can, there are only finitely many vertices. So eventually I'll have to come back to V because I can't possibly get stuck at a different vertex, because every time I go in, I have an out that I can follow. So I'm going to call that thing a circuit C1. And then what I'm going to do is I'm going to say, okay, if that circuit C1 isn't all of my graph G, I'm going to remove all of the edges in C1 and delete all the vertices from G. And then of the remaining vertices, I'm going to delete the ones that have degree 0. And then since any vertex in C1 has even degree, all the remaining vertices have even degree, and if there's anything left, what's left, which is in this graph G1, since the original graph G is connected, G1 and C1 have to share a vertex, so they have to be connected too. And then I'm going to repeat this process. So if they share a vertex U, I'm going to start at U, I'm going to follow a trail until I can't follow the trail anymore, and I must come back to U. And that's another circuit, and then I can join the two circuits and then repeat this process. So what do I mean by this? Let's see an example of what's going on in this proof. So for example, suppose my graph looks like this, okay? And this is my start vertex V. So what my proof says is start following a trail at V. And so maybe I just start, oops, I wanted to do that in pink. So maybe when I start, I go here, and then I go here, and then, so I'm not stuck here because I have even degree. Okay, so that is my first cycle, and this is the cycle C1. And then when I think about the graph G1, I'm going to remove all of the edges from this cycle. And so what I get when I do that, so G1, well, I'm going to remove the edges. So if I remove the edges, then I have no edges there, and I have these 4 edges here that I haven't used, and I'm going to remove all the degree 0 vertices. So I get rid of those 2 as well. And I just have this, and then I see this graph G1 does intersect my original graph G in a vertex, and that vertex is the vertex U. So now I'm going to start, maybe I'll do it in blue. I'm going to start following a trail here, and I don't get stuck at any of these vertices until I come back to U. And then, what is my final circuit going to be? How would I glue these together? Let me see, can I glue them together in green? Yeah, so what I would do is I would follow my first circuit until I get to the vertex U. Then I'm going to do my second circuit all the way around. And then that brings me back to the first circuit that got interrupted, and I finish it off, right? And so then I have a circuit, and now if I had something left in my graph G, I would delete this circuit. I would sort of look at what's left. It would have to intersect this circuit that I already have. I'd find a loop around, and I'd keep adding them on like this, okay? So you can also look in the book. This is theorem 10.1.4 in the book. All right, that is it.